Have you ever wondered why your hair stands up after rubbing a balloon, or why atoms hold together? The answer lies in one of the most fundamental laws of physics, Coulomb's law. Today we'll explore its discovery, its mathematical beauty, and even where it breaks down. In 1785, Charles-Augustin de Coulomb used a torsion balance to measure the force between charged spheres. He found something remarkable. The force was proportional to the product of the charges, and inversely proportional to the square of the distance between them, just like gravity. But with a twist. Charges can repel as well as attract. Here's the general expression of Coulomb's law for a set of m-charged objects.
Jesus Christ.
Don't be afraid of this equation. It's just a modern expression of Coulomb's law. These objects may be macroscopic, like spheres, or microscopic charged particles. Let me explain every term of this equation. As we can see, it is a vector quantity representing the sum of individual Fij vectors. This equation defines the net electrostatic force, Fi, which is the vector sum of the forces exerted by the J's charged particles acting on the I charge. This expression allows us to determine what is the total force on particle I due to all other particles J. The answer is this equation. The K value is a constant of proportionality, and its value depends on the unit system used. In the International System of Units, SI, its value is 1 over 4 times pi times epsilon, which is approximately 9 times 10 to the power of 9. In the CGS unit system, the constant K has the value 1, and it is designed to simplify the laws of electrostatics. The presence of the values Qi and Qj in every term of this expression means that the electrostatic force always acts in pairs, and also implies that these two bodies must have some charge in them, because if one of these two were neutral, then the force that acts on each other would be 0, even if one of them would have charge. These Qi and J implicitly carry an important principle called charge quantization. This means that every charge Q is a multiple of a fundamental value E. Because each force term Fij is dependent on Qi and Qj, it follows that the force term is also dependent on the square of the fundamental charge, E. Now looking at the fraction with these Ri and J. The Rj is the position of the charged object that acts on the I object. That is, the Ri is the position of the object that feels the action. The position of those two objects must be different by mathematical necessity, because if don't, the math breaks and the vector expression is undefined. Additionally, the charged object I doesn't exert a force on itself. This is why in the sum I is different from J. The force F is exerted by every charge in the M-charge system, except for charge I. You might be wondering, if Coulomb's law is proportional to the inverse square of the distance, why does this expression use a cubic term? This occurs because the expression includes a hidden unit vector U to indicate the direction of the relative positions Ri and J. The unit vector always has magnitude equals 1, and that doesn't affect the intensity of the force F. Now let me show you an example of how to apply Coulomb's law. The system is composed of 3 charged particles. The first, on the left, has a negative charge, negative E. The second on the right has a charge of minus 2e and is located 2 units of distance away from the first. Finally, a third particle with a positive charge E is placed between them at a distance x from the particle on the left. To analyze this system, we must ask 2 important questions. The first is, what is the net force that the charges on the left and right exert on the middle charge? And the other is there a position x where the third particle is stable, meaning a point where the opposing forces cancel each other out? To answer these questions, it is also important for our calculations that these 3 objects must be at rest. If they were in motion, the position vectors r would become functions of time, and Coulomb's law is strictly applicable to electrostatic cases. When you observe the system, pay close attention to the directions of the forces acting on it. The force exerted by the left particle acts in the negative x direction, while the force from the right particle acts in the positive x direction. This occurs because the middle particle has an opposite charge relative to the other two. Because opposites attract, the middle particle is pulled toward both the left and right charges simultaneously. Now, applying Coulomb's law to the middle charge Q3, we have the electrostatic forces on it due to the other charges. This is the equation for the forces acting on charge Q3. Note that the expression is a function of the fundamental quantity E. If we examine the domain of this function f closely, we see that it is undefined at x equals 0 and x equals 2. Why does this happen? The answer is simple. Those x values represent the exact positions of charges Q1 and Q2, and it is physically impossible for Q3 to occupy those same coordinates. Now, let's address the second question regarding the equilibrium position. To find it, we must set the expression inside the parentheses equal to 0 and solve for x algebraically. This is the solution that satisfies the expression inside the parentheses and where particle Q3 becomes stable, as both opposite forces due to Q1 and Q2 cancel each other out. Let's see the graph of the force F2. This is the graph of our function F3. Observe that at the 2 points where x equals 0 and x equals 2, the function is undefined, and there are asymptotes, in orange. The region between these two asymptotes is where the charge Q3 must be located. Looking carefully, we can see that the blue curve intersects the x-axis. This is where the two forces Q1 and Q2 become equal, and Q3 reaches a stable equilibrium. If the charge moves a little bit to the left, the intensity of the force due to the left particle is much greater, and the third particle tends to move toward it. On the other hand, if we move the Q3 charge to the right, the system is no longer in equilibrium, and the second particle tends to pull the middle charge toward it. So where does that leave us? We've seen that Coulomb's law, the famous inverse square relationship, is more than just a formula for point charges. It is the cornerstone of electrostatics. It's what allows us to calculate the forces that hold molecules together and govern the behavior of the macroscopic world around us. But as we've explored, its validity depends entirely on your perspective. In the realm of classical physics, it is remarkably precise. However, as we venture into the subatomic world, the simple point charge model begins to break down. We eventually have to pass the torch to quantum electrodynamics, QED, to account for the strange, probabilistic nature of particles at the smallest scales. Despite these limits, Coulomb's law remains one of the most successful approximations in the history of science. It taught us that the fundamental forces of nature follow strict mathematical patterns, a lesson that paved the way for everything. That's it for today. Thank you for watching. Hit the like button and subscribe for more. God bless you.